Hello everyone. Today I am going to talk about CPLD and FPGA. CPLD means complex programmable logic device and FPGA means field programmable gate array. So before going into the application and implementation and internal structure of CPLD and FPGA, so first I have to discuss about why we require these programmable logic devices. So if we are using some discrete gate and by some internal connection we are making some circuit, so if it will take a larger space for your PCB and your interconnection may interfere with other component and the PCB design will be higher cost and manufacturing time will be high if you are considering a bigger circuit. So to remove these shortcomings you can use a programmable logic device. Suppose you are using a OR gate or functionalities and functionalities or some boolean expression. By using some programmable logic device you can implement your higher number of OR gate implementation or AND gate implementation, that means boolean expression. So here logic devices are divided into three factors. One is called your SPLD, simple programmable logic device, that are divided into different categories, just like a ROM, PLA programmable logic array, PAL programmable array logic, and another type of logic devices are CPLD and FPGA. So here the first three varieties, just like your ROM, PAL and PLA, they have a input connection matrix which connect the input device to the array of AND gates, and they have also output connection matrix which connect the output of an AND gates to the inputs of OR gates which drive the output of the device. So this shows, the table shows the which one is programmable and which part is non-programmable. In case of your ROM, if you see, the input connection matrix is hardwired, that means you cannot change and the user can modify the output connection matrix only. And in case of your PAL, the output connection matrix is hardwired and the user can modify the input connection matrix. In PLA, the user can modify both the input matrix and output connection matrix. So this table shows the different connectivity, that is input connection, that means in your AND array, and output connection, that is your OR array. So this is the generic symbol or block diagram of any PLD. This is your input and this is your AND array and this is your OR array. So this AND array may be programmable and this OR array may be programmable, depending upon which type of device you are going to use. So this symbol shows how the inputs are connected to the source, just like your ABCD, and this is your AND. And if you all the fuses are connected, then at the output you are getting ABCD. Suppose if you want to get only B and C, so B and C will be connected through that fuse and A and D are disconnected, just like only B and C will be at this output. So similarly OR notation, so this is your OR notation, A, B, C, A or B or C. So similarly the equivalent circuit is A, B, C and output will be A or B or C. And if there will be no connection, so there will be no crosshair here for the second diagram, C is not connected, so output will be equal to A or B. So AND plane, similarly AND notation, you have a cross sign, and so output for the second one, C is not connected, so output will be A and B. Now let us take an example of your PLA. For this PLA, F1 is given and F2 is given, and so how to implement your F1 and F2 by changing the input connection. So according to this combination, you just use your AND plane and output will be OR plane. So make that connectivity for this operation, just like your 3 input PLA. Here A, B and C is connected here, and from this inverter output you are getting A bar, B bar and C bar. So according to this Boolean expression, you make that connection by using a symbol cross here. Cross will represent your connection. So if you don't put any cross, that means there will be no connection. At the output you will be getting that expression according to your connection. So this is your simple 4 input 3 output PAL structure. Here programmable AND array is shown here. This is your programmable AND array, but fixed OR array. So the output for your PAL structure, the output array, that means OR array will be fixed, but input array will be programmable. That means it is, you can change, user can change this input connections. Next come to our CPLD. So here by using this type of PAL and PLA structure, you need a larger connection and you need huge number of OR gate and AND gate. So to remove that shortfall or to remove that problem, we can use a compact IC where we have used a PAL-like structure. So here the general CPLD structure is shown in the figure. Here PLD represent your PAL-like block. PAL-like block is nothing but some some of these macro cells, just like your AND structure and your OR gate, and the output of this OR gate will move to some PAL-like block. So here you have a PAL-like block, that is your OR plane will move to some XOR gate, and XOR gate basically make the inverting or non-inverting buffer function. Then there will be some flip-flop for the storage of your output. So each output is programmable as a combinational, or it may be your registered, or it may be sequential, and also has a programmable output polarity. So here input is PAL CPLD, internal connection is shown in the figure. Here LAB basically represent your PAL-like block. Different type of LAB as there, LAB A, B, C, D as shown in the figure, and PIA represent your programmable interconnect array. So depending upon your requirement, this PAL-like block can be used, and inputs outputs are used here, and system clocks, obviously system clocks are there for your sequential operation. So this is your example of your one example of CPLD implementation function. F is given and x1, x2, x3 up to x7 are the input, and this is your connection, and after this is your connection, and you have a PAL-like block here. Here XOR gate used to make inverting or non-inverting buffer. So at this output side you will be getting the output of your flip-flop. The flip-flop is used for your storing your output value. So this is your simple CPLD structure, and next we move on to our another architecture, that is your FPGA. So here the basic difference between your FPGA and microprocessor and microcontroller is that in case of your microcontroller, just you have learned 8051 microcontroller or 8085 microprocessor or 8086 microprocessor. In that case, all these ICs are 40 pin IC. That means all pin has some dedicated functionality. You cannot change the function of any pin. That is the biggest restriction for using your microprocessor and microcontroller, and you cannot change the number of, or you cannot enhance reduce the number of pins if you require much more functionalities apart from its internal functionalities of your microprocessor and microcontroller. So that shortcomings or for that problem can be nullified or can be overcome by using our FPGA. So FPGA, you have a large number of pins, and depending upon its internal logic block capacity, you can implement inside your FPGA a microprocessor and microcontroller. Suppose if you want to implement in your design, suppose you need 5 microprocessor, just like your 8085 microprocessor. So you separately connect that 58085 microprocessor. But if you implement that microprocessor inside your FPGA, so if you just increase the number of pin, that means 5 microprocessor means 5 into 40, that is 200 pins are required. So you use some larger number of pins of FPGA above 200 and just write down the code of your 8085 microprocessor and just use that single FPGA. That single FPGA will function for your 5 microprocessor. So in this way you can reduce the size of your this system, as well as it will be a cost effective. So let us move on to our FPGA structure. FPGA will consist of your some interconnection switch, that is programmable switch, and our logic block. Logic block basically called a configurable logic block, and there will be some IO routing through this IO block. So depending upon your requirement, your logic block can be used, and this IO in pins are connected through this IO block. So here this lookup table inside your FPGA, that means logic cell configurable logic block, you have some lookup table. Here in this 2:1 two input for your 2 inputs lookup table uses a 3 mux to implement some functionality of 2 variables. So this is your lookup table approach. Here 2 function f1 and 2 marks are used here. Suppose in the next slide, this one, we are taking some example. x1 x2 is 0, f equal to 1, x1 0 1, f equal to 0, x1 0 0 1 1 1. So when you are putting x1 0 x2 0, x1 0 means this channel of max 1, channel 0 of max 1, and this max 2, that means the channel 0 of this max will be selected. So that means first lookup table, that means first cell of your lookup table will be selected. So the f will be equal to 1. You put here in the first entry will be equal to 1. In the similar way, that next entry will be 0 0. Let us take in last one. Suppose x1 1, x1 and x2 will be 1 1. So x1 1 1, that means the channel 1 will be selected for this mux, and channel 1 will be selected for this mux, and so that the last entry of this lookup table will be selected. So in this 3 input lookup table we have the same example. So you have 7 2x1 mux and 8 storage cells are required here. So depending upon your requirement, you can change your value of your lookup table. So this is another example how to implement some function by using this FPGA. So here 2 input lookup table to implement the function of f. F is nothing but f1 plus f2 is given. So the first x1 and x2 through some switch matrix is connected to some logic cell, that is denoted by f1, and another logic cell will be f2. The output of both this f1 and f2 are odd here, and after getting the odd value we are getting the final value of f. So f will be equal to f1 or f2. So in this way you can implement our FPGA functionalities. In the similar way, if you increase the number of variable you are using, or you can associate with the more number of logic cells. So what is an FPGA? So here basically FPGA will provide some logic block, so that will be treated as a simple standard components of your system. An FPGA integrated circuit contains 64 to 10,000 identical logic cells, and that cells can be treated as a standard component. Standard components, it may be your OR gate, AND gate, NAND gate, any of these gates can be considered. So, and the interconnection will be programmable, so the user can change that program. So array of logic cells and interconnection from fabric of basic building blocks for logic cells, so logic circuits. So first you have to write the program. First you have to write your code for by using a VHDL or Verilog, and you convert that code and download that code. According to that downloading code, your processor, that means your FPGA, will work or redesign itself internally for your written code, and accordingly it will give that output. So why it is called field programmable? Field programmable means where this FPGA program can be changed by user, not by manufacturer. That is very, very important. Suppose if your system is in the field and manufacturer already sold that product to you, and you can change the program according to your demand without the help of that manufacturer. That is very, very important. So that's why it's called a field programmable logic device, a field programmable gate array. And so these are the application of your FPGA. So the FPGA basically used in security system, video image processing, aerospace and defense, wireless communication, medical electronics, scientific instrument, and distributed monitor systems. So these are the application of your FPGA. That's all. Thank you.